Everybody, and welcome to our next video. So for section 3 out of unit 3, today we're going to be taking a look at two topics, but they're both directly tied tied together. And that is the idea of concavity of a function's curve. And then we're going to use that idea of concavity to help us carry out what's called the second derivative test. So let's dive in here. So concavity, it's a phrase that's popped up every once in a while in your algebra classes. You may have heard concavity referred to when talking about the direction that a parabola opens. Either opens up is referred to as concave up, or opening down can be referred to as concave down. So it shouldn't be a totally brand new concept, but we are going to be looking at it through a different lens, and that's the lens of calculus, like everything. So we'll go back and recap a little bit here or there. But determining whether a function is increasing or decreasing, that's what we did last section, is really just one important aspect of describing the curve of a function. But another is how quickly or slowly that curve increases or decreases. So in other words, the acceleration of the curve. That is really a really important part. And without that second piece, we can't really get a clear picture of what a graph looks like, because just knowing that a function is increasing doesn't tell everything. That could mean that it's a linear function, it's increasing at a constant rate. It could mean that the graph is very steep, but increasing, or it could mean that the graph is very flat, but increasing. So just knowing it's increasing or decreasing does not tell the whole picture. So what does is when we couple that idea with concavity. So concavity of a curve refers to the general shape of the curve. And when we know what kind of concavity the curve has and whether it's increasing or decreasing, we can describe exactly whether the curve looks like it's speeding up or slowing down. So that's the big idea here. When I have a curve that is increasing, but it starts to flatten out as it does that, so it goes from very steep to flattening out. That's the idea of this curve is increasing, but it's slowing down how fast it's increasing, and we're actually reaching a special point up top here. And then we change directions, and now we're decreasing, and it decreases at a very slow rate to start, but then it speeds up how it is, how quickly it's decreasing. That general shape has a lot to do with the second derivative of a function. So a function is said to be concave upward on an interval if, when we draw it, the graph lies above all of its tangent lines in the interval. So if I were to draw a concave up curve like this guy, or actually, I'm sorry, I forgot we already have an example over here. This concave upward curve, everywhere that you were to draw a tangent line, if you draw it on any point where the graph is concave up, the tangent line will actually sit below the graph, or the graph lies up or above those tangent lines. So that's a kind of a formal definition that depends on the tangent lines. Concave downward is the exact opposite. So the curve lies below all of these tangent lines, or down from the tangent lines. So that's one way to define concavity, but we also have our true analytical definition of how we can prove just from an equation what kind of concavity a function has. So this is all this process is going to be very similar to increasing and decreasing. For increasing, decreasing last section, we had a way of testing for what intervals the graph is increasing or decreasing. Now we're going to have a similar process for concavity. So let f be a function whose second derivative exists on an open interval I. And what we know is that if the second derivative is positive for all values of x in that interval, then we know the graph is concave upward on that interval. So what this kind of implies subtly, remember there's a cycle of functions here. F is our original, this is our position. F prime is that first derivative, but remember it's the change in the original function's graph. So it's the change in position. But then we have the second derivative function, and there are connections between f double prime and both of these original guys. So now with the second guy, it tells us the concavity of f, but it also tells us the change of f prime. So when we interpret this result that f double prime is positive, if we think of it as this guy, that's implying that f prime is increasing on that interval. Or another way of saying that is that because f prime is really the slope of f, what we're really saying is that the slopes of our original functions graph are increasing on that interval. And we can go back to, or I'll just sketch a new one here. That curve is concave up on that entire piece that I just drew. So what some students have a tough time understanding sometimes is how this second relationship works, where the slopes of f are increasing on the interval the whole time. But if I were to just start here on this left side, and if we think about the slopes of the graph of f, again, this is the graph of f, at this first left point, we've got negative slopes here. So let's just, I'm going to make up something. Let's say -2. And as we progress and move to the right, now at this next point, that slope is still negative, but it's something slightly less negative. It's not as steep. So it's still a negative value, but it's closer to 0. So let's say m is -2 here. Now it's only -1. And when I get down to this bottom part, now we have a slope of 0. Remember, at our turning points, that is a critical number where the slope would be 0. If I continue to progress to new points, now on the other side, now we have positive slope like 1. And as we continue to move across this graph, the slopes are only going to grow larger and larger because the curve is getting steeper. So if we look at the pattern or the change in these slope values, it's exactly what's going on here. The f prime, or the slope of f, is increasing on this concave up curve. -2, -1, 0, 1, 2, 4. All of those values are getting larger. So it doesn't really necessarily mean that I have to be starting from positive slope and be getting more positive. It can be starting with negative slope and progress into those positive values. So that is the big connection here, that when f prime, or excuse me, f double prime is positive, it means that f prime is increasing, which means the slopes of f are increasing, which is what's going to create this concave up shape. I can do a similar thing when we have a concave down curve. And again, I could just draw any portion of that upside down U shape. Here I have a really steep positive slope. So let's say like m equals 4. And as I progress across, it's still positive because the curve is still increasing. So we still have positive slope, but the graph isn't as steep there as it was at this previous point. So m equals 2, then m equals 1. At our turning point, m equals 0 now. And now as we head into the negative slopes, or the decreasing portion of that curve, now we could see that the slopes follow that same trend. My slopes are decreasing in quantity now, 4, 2, 1, 0, -1. And that decreasing slope, or in other terms, when f double prime is negative, that implies that f prime is decreasing, which means the slopes of f are in fact decreasing. So those are the two types of concavity that a graph can have. And again, that concavity is a direct result in the change in slopes that we see as we progress across those curves. So the third option, so we've talked about when f double prime is positive, we have a concave up. When f double prime is negative, we have concave down. But there's still a third possibility, and that would be when f double prime is equal to 0. Or also, we need to think about, it could possibly be undefined, and these kind of go hand in hand. So if we think about the 0 portion, though, when that f double prime is equal to 0, that, again, thinking about these connections, we would be considering what happens to the change in the slope. Well, if f double prime equals 0, then the change in the slopes are 0. So that means that the slope of f, oh, excuse me, forgot my delta. The change in the slope of the original graph equals 0, which means the slopes are not changing either, or in any way, for a split moment in time. This is actually where we see changes in concavity, and those points go by a special name. So points of inflection, you can think of these as the equivalent to a relative extrema as far as increasing and decreasing goes. Increasing and decreasing changes, or functions change direction at these, or at those relative extrema. Points of inflection are in fact places where a graph changes concavity. So if you remember back from last section, really the first two sections of this unit, we defined a critical number as any value of x where f double prime equals 0 or is undefined. Those are also the values of x where relative extrema must occur. Remember, though, that sometimes there were some critical numbers that don't result in those relative extrema because there are possible places where a graph can have 0 slope, or the tangent line can have a slope of 0, but we don't actually change direction around those points. And so we didn't change direction, so it doesn't result in a relative extrema. But if a function does change direction, then it has to occur at one of those critical numbers. So critical numbers, relative extrema, all of those things are kind of related together in a cycle, but they revolve around the first derivative. A point of inflection is the same kind of concept, but it relates or revolves around our second derivative. So again, a point of inflection is a point where a function's graph changes concavity. So these points are special because they're where the function slope reaches its largest value for a local area. So in other words, this is where the graph is steepest at for a local portion of the graph, which if you think about the relationship that we were just talking about with f double prime being the change in the slopes of f, if you go back to last section, you think about the thought process that we went through, we found critical values of f by thinking about where f prime equals 0 or undefined. Those turned into relative mins or max for f. Well, this is really now the same relationship, but we're doing it with f prime and f double prime. So now if you kind of think about the critical values for f prime, they're going to turn in places that could potentially be points of inflection. So then when we go through the analysis part of this, we are going to turn those into points of inflection, but those are also able to be interpreted as relative mins or max for the original function that we started with now, f prime. So there are all kinds of all of these really important and meaningful connections between these three functions. There are so much behaviors and characteristics that go back and forth between them. We can gain a lot of information about one function's graph just by simply analyzing these two derivatives. So how do we find points of inflection? So we've got a set of steps here. So we're going to first, we'll have to work our way through to find f prime and then f double prime. But once we have our second derivative, then we will analyze it just like we did with f prime to find all values of x where f double prime is equal to 0 or where it's undefined. So it's a similar process to what we've already done just with this new function. All of our points of inflection must occur at these values of x. They don't have a special name like a critical number, so we're just going to refer to them as possible points of inflection. Or in these videos and in class, I'm just going to refer to those as PPIs for short. Okay, not a technical name. That's not a real math term. Just an easy way to refer to them. So possible points of inflection. These are the candidates where the function could possibly change their concavity. Once we have that list, then we're going to use our PPIs to make test intervals. So we're going to be setting up a chart. So just like we did for our relative extrema, we will set up a chart, but now it will be x's and f double prime. So we'll come up with our intervals, and then we will pick test values out of each of those intervals, and then we will check to see what the sign of f double prime is at each of those test values. That will tell us if we're concave up or concave down, and then we're going to look for places where that concavity changes. If we find a set of intervals where we go from one concavity to the next, then we will see or be able to identify those as actual points of inflection. Now, one really important thing to keep in mind, because there is the possibility of f double prime being undefined at certain values of x, there are some functions that change concavity around a value of x for which f is undefined, taking into consideration a rational function. So sometimes we have rational functions where there are vertical asymptotes, and on one side it looks something like that, and on the next side it looks like that. This graph went from concave up to concave down around this x value, but it's not a point on the graph. X or f of x is not defined at that vertical asymptote, so therefore we can't label it as an actual point of inflection. So you do have to be really careful sometimes with the language that ends up getting used. Yes, it changed concavity, but it's not an actual point of inflection. Okay. So to give yourself a frame of reference for what these graphs could look like and where graphs change direction, this is a pretty good example. We have f of x equals x to the fourth minus 4x cubed. You can see this function has two points of inflection. We can kind of create three distinct portions of this graph. Here we have the left half of a u. So this graph is decreasing. It starts off decreasing really quickly, but then it slows down and actually flattens out. So really steep to really flat. So when we flatten out, then it actually switches over and changes. So this is an example of a graph that changes concavity, but it doesn't actually change directions. So this one's kind of special because this is a case in point where f prime equals 0 at x equals 0, but it doesn't actually result in a relative extrema because it results in a point of inflection. So I went from decreasing very quickly to decreasing slowly to then picking right back up and decreasing faster and faster until I reach this point in between here where this graph is actually reaching its steepest negative slope, and we transition into a concave upward curve. All right, so now let's take a look and actually try one of these problems. We're going to kind of do two things at once. We're going to analyze intervals of concave up and downward, but then after that, once we identify all of those intervals, then we can actually decide if the graph ends up with any points of inflection. So let's dive in. So we've got f of x equals e to the negative x squared over 2 power. So if we want to talk about concavity, I have to have my second derivative. So for our first derivative, this would be a chain rule. I've got e to some power. That is not just x. So I've got negative x squared over 2 for u. U prime would give me negative 2x over 2 or simply negative x. So if I have e to the u, its derivative is e to the u times u prime. So f prime of x would be negative x for my u prime times e to the negative x squared over 2 power. So there's my first derivative. We're going to leave that alone for right now. We don't need to do anything with it except use it to find our second derivative. But now this became a function that is a product of two functions of x, a polynomial of negative x, and then the exponential. So this becomes product rule. So negative x, negative 1, e to the negative x squared over 2. Well, we already know that function's derivative because we just wrote it. So I don't have to set up a chain rule again. We just write out the exact same result that we just got. So product rule, insides plus outsides. For f double prime, I end up with my inside product, negative e to the negative x squared over 2, plus on the outside, double negatives cancel, and we would get x squared e to the negative x squared over 2 power. So now we have our second derivative. So now first we need to find our possible points of inflection. So to do that, we're going to analyze where the second derivative either equals 0 or is undefined. Undefined, let's go ahead and knock that part out. If I go back to my original function, f of x, this guy does, it's an exponential. So as long as the inside function also has a domain of all reals, then every exponential has a domain of all reals. So our u in this case is a polynomial. So this guy has a domain of all reals, no vertical asymptotes to worry about, no holes, nothing like that. Any of those kinds of discontinuities on the original function f will carry over to every subsequent derivative. So if we had analyzed the domain of f to figure out that there was a vertical asymptote somewhere, then we know automatically that is a value of x that makes f double prime undefined. So now that we eliminated that possibility, now we can go and identify the domain of f double prime. So f double prime is really just made up of the same function as f. We've got it here and over here as a factor, along with another polynomial term. So because there's no crazy issues here, our domain is all reals, so we don't have to worry about where this function is undefined. All I have to do is set this guy equal to 0 and solve. So I'm going to do that here. Set it equal to 0 and solve this guy. So this is really going to become a function that can be factored. Hopefully you guys notice that I've got a common factor of e to the negative x squared over 2. And when I factor that out, I'm left with negative 1 plus x squared equals 0. I don't like writing in that form. It's a little annoying to have those terms backwards. I like my leading term to be positive, so I'm going to flip that around, and I get x squared minus 1. That is much easier to work with because now I can see it's factorable, or we could solve it by square roots. But if I'm thinking about where this guy equals 0, once it's in factored form, remember we analyze what values of x make each factor equal 0. Well, for this first guy, e to the negative x squared over 2, I try to set that equal to 0. Remember that the parent exponential function e to the x never equals 0 because it has a horizontal asymptote. Changing the exponent doesn't change that result. There is no way for me to plug in a value of x to create this new power and then raise e to that power and make it equal 0. So this isn't possible. Logically, hopefully you guys understand why that's not possible. Analytically, if I tried to solve this equation, you would have to take the natural log of both sides to get the x variable out of that exponent. And when I try to take the natural log of 0, that is not a value in the domain of the natural log function. Therefore, this is not an equation that we can actually solve for. So this factor doesn't produce any PPIs. But x squared minus 1, if I set that equal to 0, we produce positive or negative 1. So those two are my PPIs. Those are the only possible places where f could possibly change concavity. So I'm going to take these guys and use them to generate my sign chart now. So we're going to take the original domain of all reals. Again, think about a number line, negative infinity to infinity. I'm going to stop at negative 1 and positive 1. So that creates 3 test intervals. So f double prime. So I'm going to go from negative infinity to negative 1, negative 1 to positive 1, and then 1 to positive infinity. So now we need to choose a test value within each of these intervals. Again, this process should feel very similar because it really is the same general concept of testing these values in these intervals. The only difference is what we're testing it in and then our analysis afterwards. So instead of increasing, decreasing, it's concavity. So when we go to test these values, oftentimes because of the PPI process and having to set this equal to 0 and solve, we end up with an alternate form of your second derivative. And my recommendation is if it's in factored form, use that. Just like with the first derivative test and testing for increasing, decreasing, it's always easier to analyze in factored form because then it just becomes a product of signs. The first guy, we also already know that this is never going to be equal to 0, so it can't ever change signs. So we know that this guy is always going to produce positive values. So then it just becomes, what is the sign of this other factor? A positive times whatever, that second piece is going to determine the result here. So if I substitute negative 2 in here, I get 4 minus 1, which is positive. And we know both of these produce 0. If I plug 0 in, 0 minus 1 produces a negative. And then when I plug positive 2 in, I get 4 minus 1 again, so positive result. So that was a pretty quick, easy process once we think about the pieces here. Otherwise, you're left struggling trying to substitute values into this complicated exponential, and it's just a lot of wasted time. So always take that into consideration. If you know part of this is always positive or always negative and it doesn't affect the outcome, then make sure that you take that into account. So we've got our signs. Now we think about the shape of the graph. So positive second derivative means we have concave up. Negative means concave down. And then positive concave up again. So because we had points that are in the original function's domain, negative 1 and positive 1 are points where f is defined, and we switched concavity around them, then that is why we have 2 points of inflection here. So we have a point of inflection at x equals negative 1 and positive 1, and now we need to substitute those back in here, figure out the result. Well, because x is being squared, negative and positive 1, they're going to produce the same result. So I would get e to the negative 1 squared over 2. So negative 1 squared is 1, then negative 1 over 2. So we get e to the negative 1/2 power for both of these. Now, an alternate form, you could choose to write that as 1 over e to the 1/2 for both of these guys. Either way, it's the same y coordinate. So that graph changes concavity at 2 places. Now, to help you guys really understand what that looks like, let's take a look at this function. So y equals e to the negative x squared over 2 power. Let's zoom in a little bit here. Actually, let's redefine this as f of x. And let's take a look at, whoops. So let's go to -1, f of -1, and 1, f of 1. And you guys can see here, those are our 2 points of inflection. If you take a look here, we have concave up. So one thing about the shape of the graph, remember, it's where are the tangent lines? So for this portion of the graph, if I wanted to draw a line tangent to it, it would have to be underneath. So it's not always that the entire graph has that U parabola shape. Oftentimes, a curve will only have one part of that U. It won't always create the entire thing. So, and oftentimes, like here, it's kind of mushed down and flattened out. But the idea is still the same. It still has that general shape of where it's increasing at a faster and faster rate, or it's increasing at a slower rate and then decreasing at a faster and faster rate. That's for concave down. And then we go back to basically the other half of this concave up curve. But we do switch concavity at those coordinates that we found. 0.607 is just the actual decimal value for 1 over e to the 1/2. All right, so let's take a look at another one. So for this one, same process, same end goal, but our function for this one is f of x equals x squared plus 1 over x squared minus 4. So let's dive in and find our first derivative. So for this guy, obviously f of x is a fraction. It's a rational function, so quotient rule is what we need here. So I'm going to set that up here. X squared plus 1 gives me 2x. X squared minus 4 also gives me 2x. So for quotient rule, it will be inside minus the outsides, all over denominator squared. But that gives me 2x times x squared minus 4 minus 2x times x squared plus 1 over denominator squared. So I'm going to distribute up top, and that gives me 2x cubed minus 8x minus 2x cubed minus 2x all over x squared minus 4 quantity squared. Then we can combine our like terms. X cubes cancel, and we are left with negative 10x all over x squared minus 4 quantity squared. Now, to go and take the second derivative, this is really your personal choice, what you would prefer to do, because this denominator, typically for quotient rule, it's not always necessary to set or to expand that denominator when we have a polynomial being raised to an exponent like this. So in this case, if you choose to, we could expand this and then do the quotient rule, or we could keep it in this form, but that would require us to do a chain rule for u squared, where u is x squared minus 4 and u prime is 2x. So then that results in 2u times u prime. Personally, that is my preference because I'm pretty good at using the chain rule. If you struggle with the chain rule, then it might not be a bad idea to expand this guy out. Remember, we can do that pretty quickly with our square double square trick. So we get first term squared is x to the 4th minus 2 times the product of our terms, so minus 8x squared. And then, excuse me, plus our second term squared, so 16. So that's the equivalent form of this result. I'm going to do it with the chain rule because that's my personal preference. But if you guys don't prefer it that way, there's your denominator. You could always carry it out on your own. Either way, we're going to end up with the same result. The reason why I prefer it to do as the chain rule is because it's going to preserve the values that make this denominator equal to 0, make it easier for me to see still. Whereas doing it the other way, it's going to require you to have to go back and factor this guy a little bit more. But it's up to you. So if I do quotient rule with my pieces as they are, negative 10x gives me negative 10. X squared minus 4 quantity squared gives me 2 times the original base, or u, x squared minus 4, times u prime, or 2x. So now I'm going to do insides minus outsides. So that gives me negative 10 x squared minus 4 minus, this product would also be negative. So this actually will turn into plus. And then if I collect all these pieces, I've got a 10x times 2 times 2x. So that will result in 40x squared times x squared minus 4. Now, oh, I'm sorry, I forgot my squared here. And then again, I'm taking my original denominator and squaring it. So that makes this x squared minus 4 to the 4th power. Now, another big reason why I prefer to not expand this is leaving it the way that I did. Now it should be pretty darn obvious to all of us that there are there's common factors between all 3 terms of this rational function. My a, b, and c terms all have a factor of x squared minus 4, at least to the 1st power. If you expand the denominator and then go through all that process, you're not going to see that, which means your problem is going to have a lot of extra pieces that when we go to set this guy equal to 0, it's going to make it way more complicated for you. But again, it is possible to go that route, just not what I would recommend. So now, to make this problem easier, I'm going to reduce out one factor of x squared minus 4 from all 3 terms. So what I'm left with is negative 10 times this group. So let's go ahead and distribute there. So we get negative 10x squared plus 40, and then plus 40x squared all over. And now my denominator is to the 3rd power. So then our last step here, get back to blue, for f double prime. Ooh, that was a really bad attempt at making an x. F double prime of x up top, I'm going to be left with 30x squared. So x squared and then plus 40 all over denominator to the 3rd power. So there's my final form for my second derivative. Now we got to find our PPI. So remember, for a fraction to be equal to 0, it really means that I must have 0 divided by something that's not equal to 0. So for this condition, all I have to do is set the numerator equal to 0. For a fraction to be undefined, well, that happens when I take a non-zero divided by 0. So for that type of PPI, we're going to set the denominator equal to 0. So anytime that you're going through this process with a rational function, you're essentially going to set both top and bottom equal to 0 independently and find all of those values of x. All right, now for the first part, for the 0, let's just set this numerator equal to 0. We've got a polynomial here. So 30x squared plus 40 equals 0. So I'm going to subtract 40. Actually, I'm not going to go through this process to solve. I want us to think through this a little bit logically. 30x squared plus 40 equals 0. Let's think about the graph of x squared. I have the parent quadratic function with a vertex at the origin. And through these transformations, I multiplied it by 30. So I vertically stretched it, did not change the x-intercept. And then I shifted it up 40 units. So the end result is a super skinny parabola with a vertex on the y-axis of 40. That guy never equals 0. So I don't have to worry about any PPIs from that result. So that top possibility for the fraction equaling 0 doesn't happen. But for the denominator, this goes back to the domain of the original function. The domain of this original function, again, rational functions, the only rule that you can't break is can't divide by 0. If x squared minus 4 equals 0, then I produce 2 values of x, plus or minus 2, that the function is not allowed to use as input values. And that's because those turn into vertical asymptotes. And I told you in the previous example, whenever your original function has a discontinuity, then your subsequent derivatives will also carry those discontinuities on forever. Because if there's no points on f, then there's no slope at those values of x either. If there's no points on F, then there's no concavity at those points either. So it makes sense why those discontinuities would carry over. So in this case, and through the steps of the quotient rule, we still have that same factor, x squared minus 4, in the bottom here. So when I set that guy equal to 0, we still find those two same x values. So even though we know for sure these are not points of inflection, we still want to try and identify what kind of concavity the graph has. So we're going to still go through this process, but we know right away there's no way that this graph has points of inflection. There are values of x that could potentially change concavity at, but there's no way for these to actually yield points on the graph where we transition from one concavity to the next. So at best, we have vertical asymptotes, and it changes concavity around them. So I'm going to set up my intervals, though. Same process, negative infinity to negative 2, negative 2 to positive 2, oops, and then 2 to infinity. So test values, so let's do negative 3, 0, positive 3. So in fraction form, when we're talking about the signs of our, whether it's the first derivative or second derivative, remember it's just a ratio of the sign of the top over the sign of the bottom. And in this case, we already talked about this numerator. This numerator is always going to hold a positive value. So I can go ahead and set that part up. So it's really just a matter of testing out what is the sign of the denominator. So when I plug negative 3 in, I get 9 minus 4. That's a positive. Anything positive cubed is also positive. So our final result, f double prime, is positive on that interval. We know they are undefined at these two PPIs. If I plug 0 in now, 0 minus 4 is negative 4, and a negative cubed is still negative. So that end result, whole value is negative. And then positive 3 is going to yield the same thing as negative 3, positive on bottom, so positive overall. So now if we analyze those results, we have a curve that goes from concave up, undefined, so vertical asymptote on that graph at negative 2, then concave down in the middle, another vertical asymptote on that graph, and then on the right side, the last interval, we switch back to concave up again. So knowing all of that, we know intervals of concavity are for concave up from negative infinity to negative 2, and then from 2 to infinity. And then for concave down, we know that it is from negative 2 to 2. Now, if we wanted to look at this graph, just to show you guys exactly how this looks, let's make that graph a little bit better. Get rid of these guys. So I have f of x equals, I need to put an x in there, x squared plus 1 over x squared minus 4. Let me zoom out a little bit here for you. So remember, Desmos and your graphing calculators, neither will actually show you the graph of those vertical asymptotes. I can put them in here for us, though. Let me make this guy dotted. And then same thing at positive 2. So there you can see your vertical asymptotes. So again, noticing the shape of the graph, all these tangent lines would be sitting below the curve, or the curve is above the tangent line on the left and right side. So these are concave up portions of the graph. And at those asymptotes, we do change over concavity. So up to down and then down to up. So it is still possible to change concavity at discontinuities on the graph. We just don't consider those points of inflection. So it's an important distinction in this process. All right, so now let's talk about how we can take this idea of concavity and help us figure out some more important information. So in the last section, we learned the first derivative test. Remember, the purpose of the first derivative test was to identify where a graph increases and decreases and look at what goes on in between those at those critical numbers to see if I have a slope of 0 or undefined and the graph does change directions, then that's a way of implying that a relative extrema must exist, either a smooth turn or a sharp turn. So the second derivative test still has the same goal as the first derivative test, Ultimately, our goal is to try and prove where these relative extrema exist, but it goes about it a different way. So rather than worrying on increasing, decreasing, once we fully understand the information that our second derivative tells us about a function's graph, we can use that idea of concavity to help us find those relative extrema in an actually much faster process than using the first derivative test. The only issue is there's a case sometimes where the second derivative test fails. In that case, we have to revert back to use the first derivative test. Ultimately, after we learn this process, it's really going to be up to you guys to decide. If I ask you to find all relative extrema for a given function, you technically have the choice. Use first derivative test if you want to, or second derivative test. Just know that I would always recommend using the second derivative test unless it fails. It's much easier process. The table, the process, it's much simpler. Yes, we do a little bit more calculus, but that part's typically not all that bad. So how does it work? So we're going to say let f be a function with f prime of c equals to 0. So that's an important part here. So we are going to be looking for critical numbers, but we can't look at critical numbers where f prime is undefined. And the reason for that is if f prime is undefined at a particular value of x, then so is f double prime. So if f prime or f double prime is undefined, then we can't analyze the concavity at those points to begin with. So another case where if you have a critical number and f prime is undefined, we have no other choice but to use the first derivative test. The only way that we end up with those relative extrema anyways is those sharp turn instances like a x to the 2/3 graph or even an absolute value function. So those are some special cases in which the second derivative test would not yield any kind of results for us. But if we have critical numbers where the slope is specifically equal to 0 on the graph of f, then we can analyze the second derivative value on that, or excuse me, at that particular critical number. So we're going to take the idea that we have 0 slope and pair it with either f double prime is positive, which would imply that we have concave up curve on that particular portion of the graph, and at that same value, we have 0 slope. Well, if those two things are true about a value of x, then it's a guarantee that it is a relative minimum. If I know I have 0 slope, but the second derivative is negative, then I know it's concave down with 0 slope, and so that guarantees a relative maximum must occur. But the third case is the issue. If our second derivative is also equal to 0, then that means technically the graph has no concavity at that point, and so the second derivative test fails. So what that means is we would have to go back and use the first derivative test to check whether f changes directions near that value of x that we were testing with in the first place. So it's a rare thing, but it does happen every once in a while, so we'll have to account for that if it in fact does. All right, so why don't we go ahead and try one of these. So again, you can see the directions. It's not very specific. So if I just want to find the relative extrema for the function f of x equals negative 3x to the fifth plus 5x cubed, so my first step is going to be finding f prime. So first thing I need to do, we're going to find f prime. So this gives me negative 15x to the fourth plus 15x squared. Second step, I'm going to look for critical numbers. So again, critical numbers only of the variety where f prime equals 0. So I'm going to take my first derivative and set it equal to 0. So 0 equals negative 15x to the fourth plus 15x squared. I'm going to take out a GCF of negative 15x squared because it makes it easier to solve after that, which leaves me with x squared minus 1. So taking out the negative changes signs of both. So then I set each factor equal to 0. So this monomial, remember a monomial with a variable factor to it always produces x equals 0 as a solution. And then x squared minus 1 equals 0. If we solve that, we get plus or minus 1. So those are my three critical numbers. So these are places where we could possibly have relative extrema. So if I were to go the first derivative test route, so if that's how I wanted to go about trying to figure out where our relative extrema exist. So I'm not going to actually do it, but just so you're aware, what we would need to do, this is where we would have to come up with our intervals and then our test values, and then we figure out plus or minus for each one, and then we decide did it change directions or not. So if that's how you choose to do it, perfectly fine. But if we go the second derivative route, then our next step is finding the second derivative, which for this polynomial is pretty easy math to do. I get negative 60x cubed plus 30x. And then we're just going to test to see at each of these critical numbers, what kind of concavity does the graph have. So we're going to set up a chart, but this is a different chart. It's not going to have intervals on it. So we're going to list x values, and we're listing the critical numbers as these x values. And then we're going to look at the sign of f double prime. So I would have -1, 0, and 1. No, you don't really have to go in order. I just think it's a really good idea to visually start to put together what the graph looks like in order across. So if I go to plug -1 in, so you can plug it into the second derivative in this form. I always think pulling or factoring out as much as possible makes things a good bit easier. So I'm going to factor out a -30x from both of these guys, which leaves me with 2x squared minus 1. So if you were to do that, now when I plug -1 in, I get a -30 times a -1. Whoops, didn't mean to put the number in there. Times a -1. And then plugging -1 into here yields +1 times 2 minus 1 is a positive. So that end result is a positive. So because I know at -1 the slope of the graph is 0 and it has positive concavity, I know that there must be a relative minimum at x equals -1. Quick and easy. Now when I plug 0 in, this 0 going in for x is going to make the entire thing equal to 0. So that's an issue. So the second derivative test failed there. So we'll have to take care of that. We'll come back to that one. And then when I plug 1 in, I get -30 times +1. And when I plug 1 in, I get 2 minus 1, another positive. So then a negative result for f double prime, which means concave down. And again, when I pair that with 0 slope, I know that we must have a relative maximum at x equals +1. Now, if we go back to where the second derivative test fails, and again, this is unavoidable. It will happen sometimes. It doesn't happen all the time. But if I want to try and identify what's going on here, this is where we must actually use our first derivative. So 0 is the critical number in question. So we can't just pick any test value on either side. It has to be, you have to consider these other critical numbers. So we got to pick something within each of these intervals on either side. So let's try -1/2 and +1/2. So, and again, now I'm plugging it into the second, or excuse me, the first derivative. So we're going to plug it in up here to this guy. So if I were to do that, I have a negative times anything squared is a positive. And then if I plug -0.5 in here, that makes it even smaller. So we get +0.25 minus 1, which is also a negative. So that means f prime is positive, or f is increasing to start. Then we know f prime is 0. And if I plug +0.5 in there, I get a negative out in front again. Anything squared is positive. And then 0.5 squared is 0.25 again, minus 1 is negative again. So what we get is we see here that the graph did not actually change directions. So because of that, there is no extrema at this value of x. So if you notice, if I go back to my second derivative, now we didn't actually find PPIs because our goal was not to talk about concavity everywhere. We were really focused on looking for these relative extrema, but that's still something that should be in the back of your mind. And if you look at this second derivative, if I were to set this equal to 0 and solve for x, this guy would actually turn or yield x equals 0 as a possible point of inflection. So the fact that this had a slope of 0, but we didn't change directions, the only real way that a graph can flatten out but not change directions is if it is actually a place where we have changed concavity. So it looks something like this. So let's take a look at this guy in Desmos. So we've got f of x equals negative 3x to the fifth. Whoa. Negative x equals negative 3x to the fifth plus 5x to the third power. So again, if we go through and analyze what we did here, again, we didn't look at concavity everywhere. What we were focused on were the 3 places where the function had 0 slope, or where f prime was equal to 0. So at those 3 points, if we, let me zoom in just a little bit more, you guys can tell that either the graph has changed directions or the graph went flat. So at all 3, the slope is 0. We went from negative slope to positive slope, so we had to stop at 0 slope. Here we went from very steep positive slopes to flattening out, so smaller positive slopes to eventually 0, and then we started that process up again. So positive slopes getting faster and faster, or steeper and steeper, and then we were heading towards that next turning point. So all 3 of those kind of line up with what we see. But again, this guy in the middle here, we did not change directions, but because the graph went flat, you can see how this goes from a concave down curve here in the middle to a concave up curve right after it. So that is our process for using the second derivative test to find relative extrema. Now, again, the case here where it failed, I wanted to particularly show you guys an example of this so that if it comes up in your practice, you know how to handle it. And that is not something that happens with every single one of these problems. If it was something that always happened, then I would be recommending just to do the first derivative test, because you might as well just save yourself the trouble of having to do both. Most of the time, just doing the second derivative test will get you all the results that we need. Now, one thing we didn't do, let's go ahead and finish this up. If I identify where the extrema exists, let's go ahead and find the coordinates. So I have a relative minimum at x equals -1. So then I can plug that in. -1 to the fifth is -1. So I get +3 minus 5, or -2. And then our relative maximum at x equals +1. If I plug that in, we get -3 plus 5, so +2. And again, we already had it graphed, so we can go back, just double check ourselves, -2, +2, and there we go. So those are our relative extrema for f of x.